Cool. So now, yeah, so this talk is somewhat technical, but I have a lot of pictures. So hopefully it'll make it clear for people who are not that familiar with decision trees. So I want to start just with a quick question, which is, is it, can a typographical error lead to years of extra prison time? Like, is that actually possible? And the answer is yeah, and it's actually happened. And this is the case of Glenn Rodriguez, where he was denied parole because of his COMPAS score was miscalculated. So it's a black box model. It's used heavily in the justice system. Somebody put the wrong input in. Yeah, he got denied parole. And he only figured it out afterward because his score sheet was compared to somebody else's, and he figured that out. So we were thinking, like, okay, let's see if this, do we really need to use this black box model? How accurate is this thing? And what we found out is that, well, when we compared the COMPAS score, which we had some publicly available data. So we compared COMPAS to Corals, which was our most recent decision tree method out of our lab at the time that the data set came out. We were comparing them, and we got a model out of Corals that was so tiny, we were like, okay, there's no way this could be as accurate. So the model we got looked like this. It was so simple. It just said, if you're young and male, predict arrest. If you're a little bit older and you have a couple of prior offenses, predict arrest. And this is arrest within 2 years of your COMPAS score calculation. If you have more than 3 priors, predict arrest, else predict an arrest. And we were like, there's no way this little decision tree could be as accurate as this black box model they use in the justice system, where they're miscalculating people's scores and it's a big mess. And surprisingly, it was just as accurate. So this is 10 folds of data. So each color is a different fold. And as you can see, the COMPAS and Corals models were sort of right about as accurate as each other. And we were like, okay, that's kind of crazy. Well, let's throw the whole arsenal of machine learning weapons at this problem. And it turns out you couldn't get any more accurate, right? The decision trees were about as accurate as you could get. And some of these were like really black box models, like, well, COMPAS because it's proprietary, but boosted decision trees, random forest, and support vector machines with radial basis function kernels, and again, all kinds of stuff you can't put on a slide. Whereas the Corals model is so little that I can put it in the corner of the slide and you could actually sort of read it. And we thought, okay, this decision tree stuff, this is, there's a reason why we want to keep studying decision trees. Okay, so yeah, this exemplifies, by the way, a larger phenomenon, which is that, there are a lot of situations in which these little itty bitty decision trees are just as accurate as the best black box model that you could construct. Okay, so the COMPAS model sort of started a huge debate about algorithmic fairness, but the truth is that we just don't seem to need COMPAS at all. We should just be using little itty bitty decision trees. I'm not saying we should use the one in the corner of the slide, but I'm saying, there's no reason to use these black box models. Okay, so so what I've been trying to explain to you is that, if you have tabular data, looks kind of like that, where all the features are interpretable, then, for these kinds of problems, decision trees are often just as accurate as the best black box model you could construct. For raw data, it's a little different. For raw data, it's like, computer vision data problems with images or sound waves or large text documents. For those problems, you need a neural network. Those are the only techniques that's working right now for those types of problems. But for everything else, then all the methods, all the machine learning methods tend to have similar performance, which means that very sparse models like decision trees tend to be just as accurate as the best you can get. So it really kind of like opens up this, opens the door for little itty bitty decision tree models to do really well. So that's the motivation for why I'm talking about this particular topic today. Now, decision tree algorithms have been popular since the very beginning of machine learning. And the main problem that's always plagued decision tree algorithms is their lack of optimality, because they've historically been greedy, myopic algorithms like CART and C4.5. And these algorithms construct trees from the top downward, and then they greedily prune them back afterwards. So they construct the trees like this, a top down like that. And then once they have the tree constructed, they would like sort of figure out, oh, maybe we overfitted in this part. We'll just try to chop the parts of the branches off and stuff. The problem, of course, is that if you pick the wrong split at the top, there's actually no way to undo it, because these algorithms, they just grow the tree and they prune it back. So if you actually pick the wrong split at the top, you spend the rest of the tree trying to undo the mistake you made at the top. But most people don't actually try to optimize decision trees because, if you think about the number of possible decision trees you could have, there's a combinatorial explosion in the number of trees you could consider. So yuck. It's just a really, really hard problem. In fact, if you actually want to construct an optimal decision tree, that's NP hard, and it's factorial in the number of variables. So it's like exponential. It's almost exponential in the number of variables. So you can kind of just forget about it. Like a lot of people just gave up hope and they just said, oh, we're not going to do this anymore. So what they've typically been doing, as I mentioned, is this greedy construction where they use statistical hypothesis testing to figure out the splitting and pruning decisions. So they would split the data into two pieces based on like some hypothesis test that says, oh, rain is the most important factor for whether you're going to get stuck in traffic. So they split the data set on rain. And then from there, they would try to figure out what's the most important factor here for predicting whether I'm going to get stuck in traffic. And they would say, oh, the statistical test says it's whether or not that it's rush hour, something like that. Okay, so then after the tree was constructed, they would use statistical hypothesis testing again for the pruning. So they would pick part of the tree and they would say, should I prune this to a leaf? Well, let's do a hypothesis test. Should we keep this part of the tree? And if the answer is no, they would just prune that back to a leaf. Now, so hopefully you get the idea of this is the old style of designing trees. This is not what I'm going to be doing. So I just want to give you a little bit of background on this is the whole field of decision tree optimization in a nutshell. It's actually a big field. It started in the 1960s with the first decision tree algorithms, and then to some familiar characters like CART and C4.5 from the 80s and 90s. And then it's split into at least 4 different areas. One is binding the trees to form ensembles, which I'm not going to talk about today because that's not interpretable. But then there were 3 different other branches of work. One is from the optimization community where they were trying to globally optimize trees. And as we know, it's an NP-hard problem, but these guys were going to try and tackle it anyway, okay? And then the statisticians are over here and they said, well, since we can't solve the NP-hard problem, we're going to figure out better splitting criteria so that we can, we just figure out better heuristics to do this and to try to de-bias these trees because, we're introducing a lot of bias when we do this. And how do we handle missing variables and so on? And then another branch of statisticians, more applied statisticians, tried to take decision trees and apply them to other kinds of problems like problems with survival analysis and so on. Now, this is what I think should happen is that all of these things should come together. I think that the solution posed by the optimization community might help to deal with some of the problems that statisticians identified when they were working on better splitting and pruning conditions. Because when they were doing this, they noticed that sometimes the trees were choosing irrelevant variables. And of course they were, because it was heuristics. And they noticed that the trees were performing poorly compared to ensembles. They noticed they couldn't tell how close to optimality the trees were, again, because they were doing this greedy splitting and pruning thing, which just, no wonder. And then they figured out that if you wanted to optimize AUC instead of accuracy, you needed a whole different set of splitting criteria and you had to redesign the whole thing. That's a big pain. So what I hope is that the work from the optimization community can sort of solve some of these issues. So the idea, the utopia here, is that the user picks the objective. So you, as the user, says, I want to optimize classification accuracy, or I want to optimize AUC, or I want to optimize part of the AUC curve, or I want to optimize precision or recall or F1 score or something. And then I want to regularize for sparsity because I want my trees to be nice and small, like the Corals model that I showed you. And hopefully that will solve all the issues that the statisticians noticed, like the trees won't be choosing irrelevant variables anymore because they're fully optimized. They won't necessarily perform worse than ensembles because they're optimized. We can tell how close to optimality the trees are because we fully optimize them. And we don't need splitting criteria at all because we're fully optimizing trees. So we're not splitting under any, we're just optimizing the whole tree at once. So this is my dream. And the goal is to kind of make that happen. And if we do make it happen, then, we could try to do what the statisticians were trying to do, like adapt it to handle missing data, handle all kinds of weird biases that happen in the data, and adapt it to other problems. But first we need to get that to actually happen. So from what I just told you, all this stuff hasn't been done yet. We're still working on this part, and that's what I'm going to tell you about today. All right, so let's talk about the different approaches that people have taken to this problem, which is, I believe, the most important problem in decision tree optimization. And I think it's one of the most fundamental problems in interpretable machine learning by far. All right, so let me tell you what people have done on this problem. First, people have tried genetic programming, and they've also tried neural networks. The problem with these approaches is that you're just like, randomly moving things around, and you don't know how close to optimality you are still. So you're still kind of doing something that's greedy, and you have no clue whether you've gotten to like a good tree. So people have also tried using SAT solvers. So these problems are for satisfiability, the problem of satisfiability. The problem with using SAT solvers for this problem is you need a data set that is like no noise at all. Like all the data have to be perfectly classified. And I've never met a real data set for which that actually happens. So I'm not seeing SAT solvers as being the solution to this problem, although I'm willing to be convinced. Now, since the 90s, since the early work of the pioneering work of Kristen Bennett and Jennifer Blue, they've been using mathematical programming solvers. So you have these generic mathematical programming solvers. You throw an integer program into them, and they solve it. And you formulate the problem really carefully. You can get these solvers to optimal decision trees. And so that's what these guys have been doing. And the most recent attempt at this is really good. It's called binoct, and it works crazily well. When we saw it, we were like, wow, how are we going to compete with that? It's really quite good. But the approaches that have been really taking off, that really work, are the dynamic programming algorithms that have elements of branch and bound in them. And that's what I'm going to mostly be talking about today. Now, the two leading algorithms for this particular branch of work are called DL 8.5 and GHOST. And I'm going to be talking about GHOST today because GHOST is about 3 orders of magnitude faster than DL 8.5 and it's much faster than binoct. It's the leading method by far for this problem. And so that's what I'm going to talk about. I want to point out, though, that there is quite a lot of work in progress on these topics that are sort of more recent than I can actually cover in this talk because we haven't experimented with them. But anyway, I'm gonna really talk about how GHOST works, so you'll really get the sense of how these dynamic programming with branch and bound algorithms work. Okay, so let me define the problem for you. We are trying to minimize an objective that is a function of a tree and data. So you put in data and you tell it optimize this objective over all possible trees. And this is literally over literally all possible trees that you can construct on this data. And then the objective function looks like this. It's a combination of misclassification error. So how often the tree predicts differently than the true label of the data. So it's like how often the tree predicts I'm going to run into traffic when I don't, and vice versa. And then this is the number of leaves in the tree, which is a sparsity regularization term. So we're trying to minimize this. And the solution to this, when you put in a data set, the solution is a tree. So this is an example of an optimal tree constructed on that Broward County, Florida rearrest data. This is the same data set I was showing you earlier when I was showing you the corals example. So I took that data set, threw it into GHOST, and it produced this tree over here. Okay, so take a breath. I'm going to show you how these dynamic programming algorithms work with the branch and bound. And it's actually really fun. It's actually a really, really fun type of problem to work on. Okay, so we start by taking the whole data set and putting in one leaf. putting the whole data set into one leaf. Now I have two labels here, yellow and blue. So this is like predicting traffic, predicting no traffic. And every data point here is like sometime when I was driving home from work or something. And this is the times I was in traffic, and that's the times I wasn't, or something like that. So I just predict blue for everybody. And now I create every possible decision tree with one split. And my slide isn't big enough to put all of them there, so I only put 3 of them. But hopefully you get the idea that you have to put all possible trees with one split. Okay, so now I do that recursively. I take every leaf that's here and I split it in every possible way. Okay, so you can see that this is going to grow exponentially. It's going to be huge really, really quickly. So I keep splitting, but there's a couple of exceptions where I stop splitting. So here's one exception where all the points are all blue. And so this is a pure leaf and I don't need to keep splitting anymore. That subproblem is done. Okay, here's another case where I don't keep splitting. I happen to notice that these 2 subproblems are the same. Like whatever I solve for this subproblem, I'm going to use that for this subproblem over here. So however, whatever subtree I create from this, I'm going to use the same one here. So I don't need to solve the problem twice. I can collapse that duplication so that I won't have to deal with that twice. Okay, so that's going to help. And that's actually really going to help. That's going to make my computation time much smaller. Okay, now again, I've run out of room on my slide, so I'm going to try expanding outward this time. And I'm just going to branch out, and you can see that this is just huge search space, massive search space over trees. And then once I have solved all of the subproblems for all of the different branches, I can figure out which one gave me the optimal solution after completing everything. And then I say, okay, this is what led me to the optimal tree. And I'll put that all back together into a single tree, and that is my optimal tree, and I've solved the problem. Now, you're probably thinking, Cynthia, you're crazy. Why would I ever do this? There's this huge search space. I don't want to search the whole thing. And I'm going to say, yes, you're right. I have some theorems that can help prevent you from having to search the whole search space. So I want to show you some of those theorems and what they do. So just to give you a sense of it, the theorems will tell you that you actually don't even need to search part of the space. Let's say the search space is here. This giant thing is the search space. And these theorems will tell you, you don't even need to search here, because I can prove to you that the optimal solution is not in there. And I can prove the optimal solution is not in there. So the part of the space that you actually have to search is much, much, much smaller. And so as you can see, the quality of these theorems really determines how much of the search space I really need to look through. So let me tell you how some of these theorems work. All right, so let's say that we are in part of the search space where we're constructing, where all of our trees start with rain on the top, and then I have construction on one side. So, right, I could get stuck in traffic if there's some construction going on. So I'm building this tree. I've already decided in this part of the search space that these are going to be leaves, but I haven't figured out what to do over here for this part of the tree. So what I can do is calculate how many errors I'm making in my leaves. So here I made 8 errors. That means 8 times I drove home from work. It was rain and construction, and I didn't get stuck in traffic. Okay, so I made 8 errors over here. I made 15 errors over here. And the question is, how many errors am I going to make in here, and does it matter? So let's put my objective up here. This is, again, the same objective that I was showing you earlier. So it's the number of mistakes, fraction of mistakes, plus the regularization term times the number of leaves in the tree. And I'm going to split that into 2 pieces, one for the leaves that are already fixed, and one for these unfixed leaves where I'm thinking about continuing them to make a bigger tree. Now, what I can do is create a lower bound for my objective by setting this term to 0, because the loss is always non-negative. So I can set that equal to 0 and get a lower bound. And I'm going to call this bound B. And B is going to be my hammer that I'm going to use to whomp the search space down to a size I can handle it. Okay, so the tree is always, the objective is always bigger than that lower bound, just by the way I've defined it. Now, I'm going to show you what's called the hierarchical objective lower bound. So this is one of my theorems that help reduce the search space. So let's say that in another part of the search space, I found a tree that is pretty good. In fact, in that other tree, I made 12 mistakes, and that tree is only size 3. So this is my objective for that tree. That's what I found so far. That's pretty good. That's going to be hard to beat. And in the tree I'm constructing right now, I have already made a whole bunch of mistakes. Like I've already made 15 plus 8 mistakes. And the tree is already looking like, you know, it's already depth 3. It's looking like depth 3 already. I don't know if I can beat this. So if it's true that the best thing I've seen so far is lower than my lower bounds that I'm constructing, well, then what that means is that there's no way I can extend this tree to form a better tree than the one I already found. So in that case, you know, because this is lower than the lower bound for my current tree, then I don't need to extend this tree at all. It's never going to give me an optimal solution if I extend this thing, even if I get everything right. So this tree and all of its children will never be as good as the current best tree that I've seen so far. So this is the hierarchical objective lower bound. I'm just going to put it into a theorem. So the theorem says, if the objective of the best tree I've seen so far is less than my current lower bound for my current tree that current part of the search space I'm constructing trees with, then the tree and all of its children are suboptimal. We don't need to work with this partial tree anymore. It's dead. We're done. Okay, great. Now, let's talk about another theorem. It's called the hierarchical objective lower bound with look ahead. And what we do for this one is we take our lower bound, but in this case, you know, we can just add, you know, C to both sides. This is the same thing as adding one leaf, right? Because you get penalized by C for every leaf that you add. So that's fine. You'd believe me on that one. So let's say that we're working with a tree that looks good so far. So its lower bound is lower than the objective of the best one we've seen so far. So that means there's still a possibility that this tree could be the best one, could be extended to be the best one. Like that's possible. But I'm going to tell you that when I check it, actually, if I add one more leaf to the tree, I would suffer a penalty of C, and that would bump me above the loss of the best one I've seen so far. That's not so good. So what that means is that this thing is actually going to be worse than the objective of our tree with at least one child. So if we add even one more child to our tree, it's worse than the current best we've seen so far. Okay, that's bad. So what that means is that if we add even one child to our tree, it's going to be worse than the current best tree that we've seen so far. So we don't need to bother doing anything to it because all of its child trees are going to be suboptimal. So if the tree I'm working with is okay, then even if I add one more child to it, it's dead. And all of its children are dead as well. So that helps me reduce the search space too. Okay, next one is the leaf bound. And the leaf bound tells you that you can figure out what the maximum depth is, or what the maximum number of leaves are to get to the optimal tree. So the theorem says the maximum number of leaves of any optimal child tree is less than the number of leaves of my current tree. So here's 2 right now, 2 leaves so far, plus, and then this thing, which is the best so far, minus the lower bound of my current tree divided by the regularization parameter. So this bound tells you how low you can go, right? How many leaves can there possibly be left before I know that the solution is suboptimal? So it's quite useful because it tells you you won't have to go too deep to find the optimal solution. Now, there's also a bound that leverages the inherent level of noise in the data. that you can't get away from. So let's say that there were 5 days in a row where I drove home from work and I was in exactly the same situation each time. It was the same amount of rain, traffic, all the other factors I could consider were exactly the same. So these 5 days were the same. And then 2 days I got stuck in traffic and 3 days I didn't. Now, because these points are all equivalent to each other, there is no way my classifier can classify them all correctly. I'm going to miss at least 2 of them. I could miss 3 of them, but I have to miss at least 2 of them. I can't get them all right. So how many mistakes do I make when trying to classify this data? At least 2. And that's what we call the equivalent points bound. So the equivalent points bound says that equivalent points with differing labels cannot all be classified correctly. And the minority in each equivalent group has to be misclassified. So here, 2 points out of these 5 have to be misclassified. Great. So hopefully you get the idea of these theorems and how they work. We have one more theorem that I want to talk to you about, which is the incremental progress bound, which is that each split that you make in a tree has to provide a reduction in loss of at least C. Otherwise, I can prove that when I remove that split, I will get a better solution. I will get a solution with lower loss. Now, I have to admit, I'm really excited about these bounds because they reduce our search space tremendously. I actually cut out a bunch of bounds out of this talk. So if you're sick and tired of bounds, you should be glad that I did that. But if you're enthusiastic about these bounds, I apologize to you. I cut out a few bounds from the talk. Anyway, so I want to switch topics to talk about the computational speedups we made, because these theorems are not the only trick in the book that we have. My longtime collaborator in this project, Margot Seltzer, is an expert in computer systems. And if you give her, the first time I met her, I walked into her office and we gave her code. In a few minutes, she set it up by 3 orders of magnitude. She's incredible. So this is what we've done for the trees, okay? So the first thing we did was we represented them very carefully in memory. This is how we think about the trees, like this, but to the computer, the way we store the tree is as a set of bit vectors. And each bit vector represents a leaf, and it represents the data that falls into that leaf. So for instance, this bit vector tells us that the very first data point in the data set falls into this very first leaf. So this is a case where I drove home from work where it was raining and there was construction. And so in that case, that entry is 1 because it was the first data point. And the second and third data points fell into this leaf over here, rain, no construction. They fell into that one. And so you can see that the whole data set is encoded by which leaf it falls into. And we actually never work with these trees. We actually only work with the bit vectors. And because we have our own specialized bit vector library to do our decision tree evaluations, that makes the whole thing run really, really fast. We also have a data structure that keeps track of permutations, so that if you end up with the same set of leaves in a different permutation, that's the same as like an isomorphism of this tree. It just means that you're encountering the same tree, but like some symmetric version of it. And so you don't need to consider it twice because that would like double your workload. So if you can figure out that you've seen this tree before, you never have to sort of deal with it again because you just look it up and say, oh, have I worked with this tree before? It's like, yes, I have. So I don't need to do it again. So every time we encounter a new tree, we look it up and see whether it's actually an old tree. All right. So great. So this is Ghost. It is a dynamic programming algorithm that leverages strong analytical bounds, so it can do branch and bound. It represents the subproblem as bit vectors and uses our specialized bit vector library. It uses very fast computations. It consolidates repeated subproblems so that if you end up with the same subproblem twice, you're actually only solving it once. And that solution is fed back to all of the cases where we've seen that subproblem before. And then we have the permutation map, which makes sure that we don't end up looking at isomorphisms as separate trees. And this really speeds up the computation of optimal sparse decision trees. And like I said, it's the fastest code in the world for this problem by about 3 orders of magnitude. Now, I've actually not told you also the generality of GHOST. GHOST handles very general optimization problems. In fact, you can put in any loss that you want that is monotonically increasing in the number of false positives and false negatives. So in other words, you put in a loss that increases in the number of errors. I don't know why you wouldn't want to have a loss that increases with the number of errors, but anyway, so as long as the loss increases with errors, then we can handle it. So we can handle balanced accuracy, weighted accuracy, F1 score, precision, some balance of precision and recall, whatever you like. And then we also can optimize rank statistics. Like we can optimize area under the curve, partial area under the curve. The only issue is when you're working with rank statistics, some of our theorems don't work. So you have to sacrifice those theorems, and that increases your time to solve, which is kind of annoying. But that's the sacrifice you make for wanting to do a more difficult problem. And when you change which objective you actually care about, you are going to get different trees. So this is exactly the problem that the statisticians were struggling with. You know, every time they wanted to use a different objective, they had to create a different splitting criteria. For us, all we have to do is tell GHOST, please optimize AUC, and it does it. So if you optimize accuracy, you might get one model. And if you optimize balanced accuracy, you get a different model. And AUC, you get even a different model. And literally all you have to do is just change what you ask the algorithm to do. And there's no other thing that you as the user have to do. You don't have to mess with splitting criteria, pruning criteria, nothing like that. Now, I resisted showing you a whole bunch of plots because I don't really find that entertaining in talks. And so I'll tell you what the main experimental results are, and I'll show you just a couple of slides that I'm the most proud of. All right, so the results are that we're finding very similar classification error to black box models. This should not surprise you at all, because I showed you at the very beginning of the talk that when you have tabular data, these optimal decision tree methods tend to perform as well as the black boxes. So this shouldn't surprise you at all. The second thing we found is that when you change the loss function, as I just showed you in the last slide, you get much better loss values than greedy decision trees. So in other words, what I'm saying is when you optimize, you actually get much better results than if you try to use that annoying splitting and pruning stuff, which would actually sacrifice the quality of your result. So here, we don't sacrifice accuracy with respect to the black boxes, and we're much better than if you just did splitting, greedy splitting and pruning. The trees that we get are much sparser than all of the heuristic methods. If you try to split and then prune, you're going to get a bigger tree than we do. We get an optimal sparse tree because we're actually optimizing for a sparse tree. And we're, like I said, orders of magnitude faster than the next best method. So the plots that I'm the most proud of, can you guess which ones they are? They're the scalability plots. Those are the ones we've been working really, really hard at because we know that we're optimal, but the question is how fast can we get to optimality? So I'm going to show you some results on the data set that was used for the first explainable machine learning challenge. This is a data set from FICO. So FICO provided this data set and they said, create a black box and explain it. And so we said, no, we're not going to do that. We're just going to build an interpretable model because we know we're not going to lose accuracy over the black boxes. And indeed, with this particular data set, you can actually get an accuracy as accurate as the black boxes. Okay, so all of these methods produce optimal trees except for CART. So CART is the one method I've put in here that does things that are super suboptimal. It's very fast though, and it'll get you a result that's really quick. So this is time on this axis in seconds. This is the size of the data set. For this data set, you can put in an arbitrary number of features because you can create, there are continuous variables. So you can create dummy variables by putting more and more and more splits into the data set. So we did that, and we can get over 150 variables, and CART always solves in like a second. It's like, yeah, no wonder it can solve in a second. It's because it's producing garbage. So it can produce garbage in a second. And the rest of the models actually have to solve to optimality. And unfortunately, binoct was too slow to include for these experiments. So binoct is the one that uses the generic mathematical programming solvers. And because it's using these solvers, it's just slower because the solvers are generic and solve all different problems at the expense of sort of each problem. So over here, I'm showing you DL 8.5, which is, as I said, quite a good algorithm. But it does have this exponential sort of blow up in time as the number of features increase, which we expect because it's an NP-hard problem. All right, so the question is where that blow up occurs. Does it occur when you have a few features, or does it occur when you have a lot of features? And what we want to do is make it so that we can get as many features in as possible before the blow up actually happens. Now, this is us. It's actually the Python version of Ghost. And as you can see, it really pays off not to do things in Python. When you do things in C with the bit vectors, much, much, much faster. Okay, so Python is here. This brown method is optimal sparse decision trees. This is our method from last year. And it does have a blow up somewhere around here. And then the blue one over here is Ghost. That's the method I've been talking about. So it solves almost as fast as CART, up to about 100 features before you see this blow up. And the blow up does happen, but luckily it happens later. It happens when you have lots and lots of features. Okay, cool. So the improvements are in orders of magnitude. This is the COMPASS data set, the one I was showing you at the beginning. The data from on the COMPASS course, where, as I've mentioned to you, we don't need black box models. We can use very tiny little models and get the same accuracy as the black box ones. And so here, again, I'm showing you that we're going to hundreds of features, over 100 features before this blowup occurs, which means that for most problems in criminal justice and healthcare, Ghost is able to sort of handle those problems without us cracking a sweat. I guess that's the problem with yeah, it can do it very quickly. And there is still a blow up, as I mentioned, but it does take a while to get there, which is nice. Okay, so I'm just going to show you some different trees here. This is from 4-class data set. In the paper, we have lots and lots of data sets and lots of experiments. So I'm just going to show you that, yeah, again, if you change the objective, you get very different trees, which is super, super nice. And we've been using these, the trees actually for a material science problem. We've been designing material discovery solutions with these decision trees because they happen to be really good for material science. I wasn't expecting that, but that's what happens when you talk to a really good material scientist. You find out things you didn't know before. Anyway, so just to summarize, modern decision tree methods are not your old CART. This is, just trying to get you to understand that we can do what you can do with neural networks on tabular data sets, but with tiny little decision trees without losing accuracy. And we're not resorting to greedy splitting and pruning or the methods that are from the 1980s and 90s. It doesn't seem to me to make sense that people are still using methods like CART because, computers have improved in speed over 1 million times since CART was introduced. And so, it doesn't make sense that we're not taking advantage of that computing power by using a method like Ghost, which actually solves the problem instead of just doing heuristics. All right, thank you. Okay.
Thank you so much. I put in one question there. I'm curious, you showed that Ghost tree and also I think the Corels tree on the COMPASS data set. How is the error comparison between those two?
They're all exactly the same.
Are they?
Yeah, they're all exactly the same as the compass, corals, boosted decision trees, random forests, neural networks, whatever you put on the data set. There's no way you're going to get above like whatever 74% accurate on that data set, because there's an inherent level of noise in the data set, and you just can't get past that noise level.
Okay, I have I had another question. Oh, and I hope I don't, show myself as a non-computer scientist here, but from what I understand, R can call C underneath. Is that something that can be done with this method? Have you considered doing a package that will do that?
Yeah, so we have one like that for corals. Corals is much older, right? Corals is 2018. So we actually have multiple bindings for corals. We have Python and R. We don't have it yet for Ghost because it's a brand new method.
Okay.
Yeah, if anyone's really good at making bindings, you are welcome to. We would love to have you come and help make the bindings for us.
There you go, Shalaway, that you just got a job. Does anyone else have any questions for Dr. Rudin?
Yeah, I had one. Thanks so much, Dr. Rudin. This was fabulous. I really enjoyed the technical detail. I was curious, you were talking about some of all the theories that helped make the boundaries or the search space smaller. Are you would you say that you're confident that you've covered all of them, or are there more, how do you go about this process of kind of figuring out what applies to this situation?
So the truth is that most of the theorems we derived were derived for corals. We worked really hard on corals, just sort of sitting there thinking about how we can make bounds that would tighten the search space. And we are not confident that we have all the possible bounds. There's one bound that we've been struggling with for years. We have the theorem, but we can't implement it because every time we implement it, it slows the code down because we're checking the bound so often that the checking the bound slows the code down more than the bound is helping to reduce the search space. And I feel like that bound is a major frontier that if we could actually get it to work, we could actually reduce the search space tremendously. And I bring this up continuously. I'm like, we've got to get the similar support bound working. We've got to get it working. And we listed it as an unsolved problem in the corals paper that we couldn't get this bound working. We have the bound for decision trees. We still cannot get it to work. The dynamic programming really helps, but I still don't think we quite have that particular bound sorted out. So, and if you're interested in the technical details, that bound is in the papers. We actually have the theorem. We know what it is. We just don't know how to use it. But there could be other theorems too that we haven't discovered yet. That's definitely possible. This is really, an unexplored, really important field, I feel like. And there's not that many people working on it. And most of the people working on it are in the mathematical programming community, and they're trying to use these generic solvers, which are giant beasts, and you have to tame them into solving your problem. And those guys keep making advances, but they're still way far behind us. But they have bounds too that are helping reduce the search space in their own way. Yeah, so if this is a topic that people can, what I explained to you was as deep as it gets. The theorems are what I told you they are. So anyone can jump into this and start working on it, no question. And all our code's public, so you can start building on it right away.
Awesome, thanks, very exciting.
Hi, Cynthia. Thank you for the nice talk. I have a quick question. Do you think that statisticians and generally academics working in this area are doing a disservice to their students by talking a lot about computational complexity, and that's O n squared, and that's epi hard, and big over there and small over there, when in fact, things like what you showed us today kind of prove otherwise. Instead of thinking about computational complexity, perhaps we should be thinking about, okay, how scalable it is, how does it work in practice? Can I go from 50 to 100 features? I don't really care if something's NP hard or not, or I don't really care if something is O n cube, if what I see is in practice is better.
Thank you so much for bringing that up, because that's exactly what you're exactly right. And it's haunted me for my whole career that people were saying, you can't solve this problem. It's NP hard. I don't want to touch it. And I've seen people, like you say, I'm working on optimal sparse decision trees, and they look at me and they're like, oh, but isn't that NP hard? You know, it's like that face, you know, that like that, oh, you're working on a problem that's impossible. I'm not stupid enough to do that. But the truth is that we need to solve this problem. It's one, like I said, it's one of the most fundamental problems in interpretable machine learning. And we got to solve it because we need these trees, because that's what we're going to use in practice. And that extra computation that we spend making the tree, that's going to be a policy that is used maybe in an intensive care unit to help save people's lives, maybe even the theorist's lives who's claiming that NP hardness is not, we shouldn't be solving this problem. So, you know, I agree with you. I think the theorists should just stuff it and sort of, you know, say, look, I think I'm going to respect people who are going to try and solve these problems. And to be honest, the theorists have gotten swamped by the neural networks people, because neural networks are solving problems that are just, you know, who knows what the complexity is of neural networks solving, right? They're not solving convex optimization problems. And so now the theorists are desperately trying to figure out how neural networks work, because, you know, they were sort of taken by surprise that these things actually are solving problems that make sense, rather than like support vector machines where everything is convex and you can understand what's going on. So yeah, I really appreciate your comment on that. And I really do think we should listen less to the theorists and listen more to the people who are actually trying to solve real problems in reality.
Thank you.
I love it. We have one more question in the chat if you have time. Could you talk a little bit more about when the blow up happens? Are there checks in place to check, given the data set, how many features are okay to try, something like that?
Okay, so that's also a really good question. And I don't have a good answer for that, because it has to do with the correlations between the features. If you have only a few features and they're highly correlated with each other, it's going to take forever to solve it, because the algorithm, like what it'll do is it'll find a good solution really quickly. It'll find a small optimality gap really quickly, but it'll take forever to figure out which of these highly correlated features in the solution. So when you have multiple highly correlated features, it just takes forever no matter how many features you have. If you have hundreds of features and all of them are fairly sparse and fairly uncorrelated, you could get the solution and prove optimality very quickly. So there's no real, there's no really good answer to that one, other than just looking at correlations. There are no checks in place. We don't have any, but a really great research project for anyone could be to figure out how to create those checks. And I feel like that could be something that's manageable and could really be helpful.
Jason, you got a question there?
I do. It's a great talk. I might have missed something in here, but you were talking about the putting the different boundary conditions. But then there was a moment where you were talking about like the child splits, and then knowing that you don't have to go any further. And one of the things that I'm always worried about is what happens if we have a suboptimal early split to get to more optimal later splits.
Yeah.
You know, so can you talk a little bit about that? Is that something, like, I'm always afraid of it, but I don't actually see it happen very often that I can think of, that maybe in the all solution context that you're talking about, in this concept of, well, you get the same issue when you do the different splits and you say, okay, that's the same problem in different like potential trees. Maybe that sweeps some of that suboptimality issue come up. But you know, in terms of practical implementation, you know, is this something that you run into? Is this something that we really should be concerned with, or is it just theoretical minutia?
So no, it's not theoretical minutia at all. So the way the codes work is that they'll try out that suboptimal split, and then the theorem will show up and say, can I prove that this split was suboptimal? If it cannot prove it, it will keep that tree and all of its child trees in play until it explores further down and realizes that that split created a problem that it can't undo. And then the theorems will say, nope, get rid of this split. And then that information will propagate back up to eliminate the bad split. So that's how our algorithms would handle that problem. an alternative, if the split is really bad, like let's say that you make that split and you immediately realize that when you did that, there's no way to construct an optimal tree from it, then the theorem will come in and say, nope, that split is bad. I'm going to eliminate that split and all of its children that could possibly exist. Does that make sense? Okay, great, cool. Okay, how do we evaluate the performance of the tree after optimizations? Okay, so the trees are evaluated using, okay, there's several different evaluations. The first is the loss function, like the accuracy. How accurate is the tree on the training set and on the test set? Luckily, because these trees are small, they tend to generalize really well to the test set. So training set and test set performance tend to be very similar to each other. We also evaluate the sparsity of the tree. So we usually have, in our evaluations, we have an accuracy versus sparsity plot, which I didn't show here because I just didn't want to show like a million plots. So we always have an accuracy versus sparsity plot. And we want to have the best accuracy for each level of sparsity. And then we evaluate scalability. How fast did it take us to get to the optimal solution? And then the other thing we look at is optimality gap over time. The optimality gap is the difference between the solution we find and the lower bound of it. The lower bound B that I was showing you, that formula B. So it's R versus B. And when that gap goes to 0, we know we got the optimal solution. So we look at how that optimality gap changes over iterations because we want it to get small as quickly as possible. So that's how, those are the different ways we evaluate the trees. That makes sense?
Yeah, that's great. And if are there any more questions? We'll take a quick break. Thanks again, Dr. Rudin, for coming and talking to us. I think we all really enjoyed it. Oh, there is one more question there. We need to get to break those so that we can get to trivia, but you can answer this one as we're breaking if you'd like. Is there a best order for all of these checks that you're doing?
Okay. Everybody on break. So you're welcome to break and I'll answer this question while the break is going. Yes, it's on GitHub. Yes. You can link, there's a link from my website. So just to answer that question, there are many debates in our group meetings about the order in which these things should be checked, because you want to check the theorems that are the most likely to get rid of a whole bunch of trees. And so, so that is actually a matter that is up for debate. It's an active area of research, and I'm really glad you asked that question.